All right, I believe most of the students are here. Let's just get started. So in today's lecture, we'll first wrap up our discussions on finite state machines, FSMs. This is obviously an important topic, right? We have been spending already 2 lectures on this, right? And after that, we'll start talking about delays, timing, and we'll look at what's the implication of this logic delay. And hopefully it will be soon pretty clear why do we want to make use of the clock, and also why do we want to make use of the flip-flops instead of the latches. Okay, so this is the plan for today. All right. Okay, as usual, some of the logistical items. So homework 4 is now on CMS. Right, there was a glitch, right, about the deadline initially. It's actually due on 26, I think, right, next Friday. And pre-lab, right, the second part of pre-lab for lab 2 is due tomorrow. And also it's important that you guys check CMS, right? So make sure that you guys group yourselves for the rest of the lab 2 assignments. We still have lab 2B, and also I think there's a report, right? That report. Okay, right. Just in case that you this is still not too clear to you, right? So when is the checkup? So usually there's no pre-lab for check. There's no checkup for pre-labs, right? But for for lab 2A and lab 2B, we do require checkups, and also you don't have to attend the lab hours, right? You can check out during a TA office hour as well, but usually we have more TAs available, right? In the lab hours, usually we have 3 TAs available at the same time. Okay, and also you guys probably have noticed, right? The final exam day is not available. It's going to be on Sunday, 23rd at 7:30. Good question about the length of the exam. Ethan, I haven't decided yet, but usually it's 2 hours. Okay, I'll let you guys know. Usually 2 hours. All right. Okay, so let's review some of the things that we discussed last time, right? Last Thursday about FSM. I think this is a quiz question, right? So I asked you guys to look at this diagram. This is a Moore diagram, right? So just want to refresh your mind, right? So this Moore diagram, we have a state label over here, right? So this is the output, and then in the square bracket we have the encoding, right? So we usually have binary encoding for each state. And in this lecture, you also see a decimal encoding just for convenience, right? And I'll ask you guys to come up with this transition output table, right? This is not a hard quiz, right? All you need to do is to just follow the transition, right? So in this state transition, there's a transition output table. Just want to make sure that you guys are still familiar with the terms, right? S, we use S to indicate the current states, right? And S star to indicate the next state. Current state is part of the input, right, for this extended truth table. It's really a truth table, right? And S star is part of the outputs, right, for this truth table. And of course, the actual output is also part of the output, right? If you fill out this transition output table, right, it's going to be pretty clear. Right, so this is the expression for the next state logic, right? And the expression for the output, right? For the output, it's not too surprising. And for this one, is basically XOR, right? XOR gate, which is something that we have already learned. Okay. All right, so. Okay, so what's the question? I think there's some questions, right, popping up on the chat window. Mitchell is asking, I don't think it's always S. Why is Q column for Moore machine? It's always S. It's not always. This is a question from Ethan, maybe, right? It's for this specific machine, right? For this specific T flip-flop, right? We have 2 states, right? This is the T flip-flop is composed of D flip-flop and the XOR, right? So for this specific machine, the Q output, right, is the same as the state, right? If you look at the state diagram, make sense? Right, over here, look at the state diagram. Q is 0, right? Then we are in state 0. And Q is 1 when we are in state 1. Okay. All right, so is it clear? Listen. Okay, of course, right? So no, in general, this may not be the case, right? But if you look at the diagram, this is indeed true. Okay, and Alma's asking, how about mealy machine? Very good question. Actually, you are reading my mind, Alma. So there will be an exercise. I'll actually ask you guys to come up with a mealy machine for this kind of flip-flop. Okay, we'll talk about this soon. Okay, all right, so this is the T flip-flop, right? And maybe real quick about prelim, right? There's actually a prelim question where I ask you guys to build a D flip-flop, right? Out of TFF, right? It's actually very much symmetric to how we build TFF, right? T flip-flop out of DFF. So all we need to do is to add the XOR, right? Over here on the input side. And we connect Q over here, and then this is D. Okay. So of course you can derive this. So using this XOR, this is a XOR. Okay. So of course you can derive this using a truth table, right? But intuitively, I hope this is clear, right? So what do you, so you want to set D, right? But if Q, so in this case, right? If Q is already the current state, right? Q is already same with the new input D. We don't want this T flip-flop to flip, right? So we want T to be 0. And if D is different from the current state Q, we want it to flip, right? So this is exactly what the XOR can do. Okay, so hopefully you guys get the intuition. Again, you can derive this using by drawing a truth table. Okay, so this is T flip-flop, right? FSM, we just look at more machine. This is indeed a more machine, more FSM, and we just look at the more state diagram. Right. We'll also look at mealy. We'll discuss mealy versus state again. Okay. After we look at the problem. Any other questions? Okay. If not, let me just quickly go over some of the slides that I already showed you last time. Right. We look at this table, right? Transition output table for this pattern detector. This is a more machine, right? I think I asked you guys to derive the actual expression, right? Boolean expression for the output and also the next states, right? Although I did not write down the expression for every single next state bit, right? In this case, we have 2 next state bits, right? S1 star and S0 star. Okay? And these are the answers, right? Just for your reference. It's a more machine. We also did mealy machine, right? And this is the transition output table, right? Just want to remind you guys again, right? So with mealy machine, okay, we have, right, the output here, right? So this is really the output bit, right? Because this mealy machine output depends on both the current state and also the inputs, right? So that's why the output column is pushed, right, inside. And this is the truth table, right? So one thing that we talked about last time is, right, so we are actually missing, right, if you look at this truth table, we are missing 1, 1, right? So that's why everything right on this row, in this row will be don't cares. And we can actually make use of this don't cares to minimize the expressions for both output and next state, right? Okay, again, these are just for your reference, okay, in case you want to derive this on your own and then you want to check your solution. All right. Okay, so let's look at one more problem, okay, before we wrap up FSM. So let's look at something more realistic. So here we have a traffic light controller. This is something that we are seeing pretty much every day, right? At least before COVID, right? So over here we have a fairly common traffic light, right? We have let's say we look at 4-way intersection, and we are sequencing these opposing lanes together, right? So we have north-south, right? and east-west. Okay, so we have basically 2 traffic lights, and per traffic light, so the green light will stay for 20 seconds. This assumption. Yellow, okay, will last for 5 seconds, and of course, right, the red light will last for 20 plus 5, right, 25 seconds. So this is the problem setup. So let's see how we can sort of formulate a problem, right, and then generate and convert it to FSM. So let's first try to break it down a little more, right? Like I mentioned, we have 2 traffic lights, right? But they actually change together, of course, right? So we have one for east-west direction, okay, and the other one for north-south direction. Of course, right? For EW or east-west, when screen, the other one's red. Okay. So in this case, we can, basically we can just name these 2, right? So we can group these 2 together and then form one state, right? So we'll be staying in this state for 20 seconds before we move on to the second state. This is where east-west is yellow and north-south stays red for 5 seconds. And this is symmetric, right? We have red, green, another 20 seconds, and red, yellow for 5 more seconds. Okay, so if we have to design a digital system, right, a sequential logic, let's say, out of this, what would be the clock cycle time or clock period? What is that? Very good, Emily, right? 5 seconds. Okay, makes sense, right? So, there's one cycle, basically, because this is the period, right? That this is the time interval that we use for the yellow light. And 20 seconds is a multiple of this, right? So with that in mind, we can further break down, right? So some of this sort of a super state, right, into smaller states, right, based on the clock period. Again, the clock period now is 5, right, over here. And when we are looking at this green-red state, right, we have 4 cycles, right? We basically spend 4 cycles on green-red, and then 1 cycle on yellow-red, right? And then another 4 cycles on red-green, etc. Make sense, right? So in total, we have 10 states. Okay, and here's the FSM. So we have these state bubbles, right? Let's do a Moore machine. Okay, let's just do a Moore machine. So there's a question, why is there red 1 through 5 and green? What do you mean by 1 through 5, Alma? Can you
yeah, just say it. Like, how come east and west is just green or yellow or red, but north and south is red 1, red 2, red 3, red 4?
So again, this is the period, right? So for green/red, right? So we spend 4 cycles on this, right? So that's why we named this 1, 2, 3, 4, right? And we have the yellow state, right? That's just 1 cycle. That's why we separate out, right? And for the other scenario, right? So this is where we have red/green, right? So we also spend 4 cycles on this. So again, we name it 1, 2, 4. Does it answer your question? I'm not sure where does the 5 come from.
Yeah, no, that makes sense.
Okay, Gavin's asking why is east and why not green 1, 2, east and west? Not green 1, 2, 3 in the first 4 cycles. What do you mean by we are using green 1, 2, 3, right, Gavin? Can you clarify your question?
I think it is the same question that was just asked, but basically the question is essentially, if you look at the first cycle, red has like a 1 after it for the north and south. But the question is just like, why does green not have the label 1? Or is that just kind of, that's kind
I
of
see.
insignificant?
Okay, I got your question. Okay, good question. So we are basically treating this whole thing as one label. Okay, and then add a 1, right?
Okay.
Later on, we'll just call it green. Okay, we'll soon use a shorthand. Okay, good question. Yes, basically we have green 1, green 2, green 4, right? Green 3, green 4 as well. But I'm just treating this whole thing, right, as a whole. Okay. Any other questions? If not, so okay, here's the shorthand, right? So I'll just do G/R, right, to indicate green/red. Okay, again, I'm only adding 1 number over here. Then we basically have a cycle, right, with 10 states, and this is just a circling, right? This is a Moore machine, right? I'm using this, right, this figures to indicate the outputs, right? Of course, in the actual circuit, we do need to have separate wires, right, for different outputs. So, this machine looks simple enough, right? But here's my question to the class. What is this machine modeling? This is FSM, right? This is actually modeling a sequential logic, sequential circuit that you guys are familiar with. What does this one do? If you just look at FSM. Very good. Counter, right? Can be more specific? This is just right, you have learned something called free running, right? This is just a free running counter, right? Of course, depending on where do we start. So in case this is not clear to you guys, right? We can just come up with the state encoding, right? We have 10 states, right? How many bits do we need to come up with a binary encoding? How many? 10 states. Okay, 4. Okay, very good. You can just do this, right? If you look at the sequence of this state encoding, right? If you do this way, hopefully this is clear to you, right? We are basically just doing right. We're just doing the counting. Right? Make sense? All right. Okay. So, is there any redundancy in this FSM? Right. So Peter is already asking this question, right? So can we do better? Right. This is sort of a symmetric, right? So the east-west, right, and north-south, right? They are symmetric. So we are seeing some redundancy, right? By redundancy, I mean you look at this part, right? So we are counting up to 4, right, before we turn yellow. And over here, we are also counting up to 4, right? Before we make the transition, right, from this red-green state to red-yellow state, right? Hopefully this is clear to you guys, right? And there's some symmetry that we might be able to exploit to further minimize, further simplify our state machine. Of course, the question is, how do we do that, right? So if you only use actually one FSM, this seems hard. Okay, but first of all, right, before I talk about other things, is it clear? Is this diagram clear? Okay, cool. So, and later on, right, in the rest of the slides, I'll just call this green state. These are just green states, okay, because there's the green light, right? Whether it's in the east-west or north-south direction, these are green states. Okay, and one more thing. Okay, is there anything missing? Right, we have the state label, right, with output, right, and it's more diagram. Something is missing on this transition arc, right? what does this mean? There's nothing on this transition arc. No inputs, right? Basically, this means that actually, whether there's input or not, when you guys see a transition arc like this means unconditional transition. Okay, so we also use it for other FSM as well in the next few slides. Right, basically regardless of the inputs, whether there's no inputs or there's inputs, right? So if we are at this state, right, we are going to make next cycle, we're going to make a transition. Right, if you're at this state, right, next cycle, regardless of the input, we are going to make a transition to the next state. All right. Okay, so now let's look at how we can make use of this symmetry, right, to simplify the FSM. So to some extent, this is like, this is not a precise analogy, but if I have to give you an analogy, right? So, if you see expression like this, right, you see that A is common, right, in two terms. You sort of want to do this kind of factoring, right, to simplify the Boolean expression. So can we do that? Turns out that for FSM, we can also do a similar kind of factoring when we do have common parts, right, in one single monolithic FSM. If there are like common parts, we can do some factoring, and we actually break it down into more than one communicating FSMs, right? Basically, these FSMs will be smaller. Each of the FSM will be smaller, but they will be communicating with each other. So in some cases, actually many cases, these will result in simpler FSM and with at least fewer states. Okay, so let's see how do we do this for this traffic light controller. So we break it down into two FSMs in this case. So the first one is pretty obvious, right? Well, actually, the second one is pretty obvious. So depending on which I'm looking at, if I look at this diagram, right? So this is the first one, the on the left. The timer one, we already discussed this, right? We are seeing this asymmetry. We are counting up to 4. So we can just create FSM for this kind of counting behavior. We just call it timer. This is also the one that you guys are building for lab 2, right? You're also using counter to build a timer. And the other one, so is where we try to simplify things. So instead of looking at, if you look at the previous state diagram, right, with the 10 states. So each state encodes both the traffic light information, right, whether it's green, red, or yellow, and it encodes the time to some extent, right? So what we are trying to do here is we are trying to separate out the concerns. So we have a dedicated timer to manage the time, and then we have another FSM called light controller. So this FSM basically just manages the state of the traffic lights. And of course, we only need 4 states, right? Okay, so these are the 4 different scenarios: GR, YR, right, RG, and RY. So once we have this separation, right, once we have this decomposition, you can see that we end up with only 8 states. Make sense, right? So 4 states for the light controller, we'll call it LC, and 4 states for the timer. And of course, these two need to interact with each other, right? So when we count up to 4, the timer needs to tell the light controller to advance to the next state, to the next scenario. And also the light controller also need to tell the timer, right? So what's the current color of the light, right? So is it green? Is it showing green or not? So these are the 2 signals that are being exchanged between 2 FSMs. Okay. Right, so there's a question, why is 4 state, not 5? Does the number of states change if you think about it as a milli or more? Good question, Alma. Yes, so we're going to talk about this. So the number of states may change depending on whether we are doing milli or more. In this case, we are doing more, right? And hopefully, at least you agree that we only need we need at least 4, right? We need at least 4 states, but turns out this is just sufficient, right? Since we are doing counting, right? We can quickly wrap around. We only need 0, 0, 0, 1, 1, 0, 1, 1, and then we wrap around. We go back to 0, 0. We only need 4 states. Make sense? Okay, again, we are going to talk about the difference. We're going to talk a little bit more about the difference between mealy and more, and what's the trade-off and implications. Okay, so maybe let's take a closer look at these 2 FSMs, right, before things are hopefully clearer, right? So one more time, we have 2 FSMs, right, and they are communicating with each other. So let's look at this LC, the light controller first. So this is where we are taking this next. We have a next signal from the timer. This is where the timer says that you need to advance to the next scenario if it's 1. So you look at this state machine. So we have 4 states, right? 4 scenarios. We are going to be staying, right, in this green states, right? So we have 2 green states, right? GR and RG. So we're going to be staying in this green state for at least 4 cycles, right? And this is where the counting, right, is happening in the timer. Right? The timer is counting. So basically, in the first few clock cycles, the timer will just say next is 0. Basically, do not advance, right? Until the timer says that now it's time to advance. So we go to this yellow and red state, right? YR state. And we go to this RG. Why is there no input label here? Any ideas? We just talked about this. Why is this an unconditional transition? Why is that? Why are we not looking at next? Because, right, because very, very good, right? Because this state is just 5 seconds, right? This state is supposed to just stay for 1 cycle, last for 1 cycle. That's it. So basically, the timer is supposed to tell us next to be 1, but it doesn't really matter. We need to make the transition anyway to the next green period, right? Okay, and then we stay over here for a few cycles, and then go to another yellow state. Right? Is it clear? This is the light controller, right? And one thing that the light controller will output is this one. Oops. This one. The light controller will output green. So green is the signal that we send to the timer. So when we are in the green states, right? We have 2 green states, right? We set this green signal to be 1. Otherwise, we set green signal to be 0. Also, just want a quick note that, right? See here, so these are the encodings I'm using for this specific FSM, just for the sake of convenience. Because later on, when I show you guys the timing diagram, I'm not going to show you the binary encoding. Right? I'll just show you the decimal encoding, but you can easily translate it into binary numbers. All right, so this is the light controller, and this is the timer. The timer, basically doing counting, right? Nothing is really too surprising, right? In this diagram, we have this, right, unconditional transitions, right? So we count 1, 2, 3, right? But over here, this is the interesting state. So this is where we have something called G4/NG. The meaning is this is the last green period, as indicated by G4, right? The 4th cycle. And also, we actually spent 1 more cycle here waiting for the yellow light. I guess this is why, Alma, you were asking, right? Why are we not having 5 states? And this is actually the trick, right? So basically, we stay in this G4/NG state for 2 cycles. In both cycles, we output next to be 1. Okay. Basically, for G4, at G4, the last green period, we say like the LC, right, the light controller should make the transition to the yellow state. And we wait for one more cycle over here until we actually see the light becoming yellow. And then we make the transition. So that's how we save one state. All right, is it clear? So this is the timer. All right, so if this is not too bad, right? So let's just look at the waveform. Again, I'm using the decimal encoding over here, and this is the output, right? So when we are counting, right, when we are counting up to 4, the next is 0 until we are at the 4th cycle. So that's where we say next is 1, and we say next one to be 1. We say next to be 1, right, in one more clock cycle. All right, so this is the waveform. So we have the clock, right? See that indeed the clock period is 5 seconds, right? So these are labeled, and we have this next screen, right? So here we start out with state 0, right, for both LC, the light controller, and timer, and you can see the pattern here, right? The LC, the light controller, will stay in state 1, which is the green state, one of the green states, for 4 clock cycles. And the counter, the timer, will count, right, up from 1, 2, 3, 4, and then stay there for one more clock cycle for the yellow light, and then we repeat. Okay, and we repeat. Okay, is this one making sense? Okay, so that's how we end up with just 8 states. We get 4, right? So we get 4 scenarios for the lights, and then we get 4 states for the counter. If this is still not too clear, right? So let's look at I have a few animated slides, right, to help you guys walk through the state transitions in both FSMs. Right? So again, first we start out with this state 0, right? In both, these are the highlighted states, right? In both FSMs, right? And then we move on, right? We start counting, right? So this is where we have the light controller, right? And we have the timer. So what do you think is what are the next highlighted states, guys? In this cycle, in the next clock cycle over here. And guess, does the LC, the light controller, changes its state? Yes or no? No, right? Because we are counting. How about timer? Timer is going to advance to G2, right? Okay, very good. So we move the timer. Okay, next cycle, we keep moving the timer right to the next state, and next cycle we keep moving, right, until we come up to 4. So this is where we set next to be 1, right, over here. We set next to be 1, next high here. Once the light controller sees the next light signal, it's gonna make the transition. Right? Next cycle, the light controller will make the change, right? Will change its state to YR. And the timer will stay for one more clock cycle and wait for the yellow light. Right? And it will continue. All right. So this is the traffic light controller. Any questions? Okay, great. Very good. So this is the last problem that we want to solve, right? So in the lectures, in your homework, I'll give you guys a few more questions, a few more problems, so that you get more from this FSM. It's indeed an essential topic to master for the understand digital system, especially sequential logic. Okay, so I'm gonna ask you guys to answer a few questions on item 2 before we discuss a bit more about FSM, MIDI, and more. Okay, please go to item 2. As usual, go to ECE2300 Live. Just for your convenience, here's the link. All right. These are a few good questions for you guys to refresh your mind about the very basic definitions of some of these key concepts that we have covered so far. Okay. So let me also share the screen so that you get to see the response live. All right. We are looking at the first question, right? And just as I expected, we are not seeing consensus for some reason. Okay. Let's see. Cool. I think some people are changing your mind. All right. So let's see what's the answer, right? So the question is the next state in more FSM only depends on its current state. It's a more machine, right? The answer is, so first let's see. Right, so interestingly, right, the majority of the class chose A, right? Actually, this question is a little bit deceptive, right? So I'm not asking you guys about the output of the Moore machine, right? I'm asking you guys about the next state of the Moore machine. So it depends on both current state and inputs, right? Make sense? So this is actually false. So good job if you guys got the correct answer. Next one. Let's see whether there's any questions on chat window. This is not a quiz, okay? This is not a quiz. This is just a set of in-class exercises. With the quiz, I'm not going to review the answer. Next one. Next state logic. Next state logic in media machine, in media FSM is combinational. And true or false? I think the class is converging to one of the answers. All right, let's see. Okay, good job, guys. Right, most of you got it right. So it is indeed combinational, right? Because last time we talked about 3 blocks, right? 3 always blocks that you guys have to write to describe the FSM in the Verilog, right? In Verilog. So output logic, next state logic, and the logic to update the current state. The only sequential one is the logic where you update the current state. You basically assign the next state to the current state. The next state logic is indeed combinational. Okay, last one. Hopefully this one will trigger some more discussions. The function of a DFF can be described as a mealy state diagram. Well, interesting. Okay, so indeed, most of you are believing in one of the answers. Right, pretty much most of you agree. which is good. Okay, which indeed is going to lead to some more discussions, I hope. All right, so let's see. Answer is yes, right? That's good that most of you got it right. And we're going to discuss this, right? I know a few of you are, maybe having this question, right? So FSM, the FSM for the D flip-flop is indeed more, right? Why can we use it? Why can we use a Mealy state diagram to represent it? Let's just try to work it out. Okay, let me come back to my other screen. Okay. First, any questions about the first two questions? First two problems. Okay, if not, so I'll ask you guys to do one more exercise. And this is actually related to the question that Alma asked at the very beginning. So can you guys give me the, we already know the Moore diagram, right? So we already know for Moore diagram, so we have something like this, right? For DFF, okay, we have two states, right? S0, S1. So we have this, right? We have 0, 0, right? 1, right? What should be on the arc? So we have 1. Sorry, we are drawing. I have Mealy machine in mind. I asked you guys to draw Mealy machine, but we are actually drawing Moore machine, right? Okay, so this is the Moore, right? Moore diagram. Can you guys give me the Mealy? Can you guys spend a minute or so to draw a Mealy on your own, and then we discuss? Okay, good news for you guys. No quizzes today in this lecture. This is Moore, right? What are Mealy? So I'll ask guys in maybe 20 seconds about the diagram that you drew. All right, so how many states do we have for Mealy? 1, okay, right, interesting. Okay, most of you agree, think that we only need 1 state, right? Okay, so let's say we have 1 state. Just S, right, at 0. Okay, so what do we put on the transition arc? We don't output anything, right? This is just 0, the state encoding. What do we put here? 0, 0, 1, 1, something like this. Is that right? Okay. Some already are saying 2, right? But let's first focus on the answer, right? From the majority of you others on the chat window. So you believe that this is just a single state. So with this diagram, guys, can you tell me what's the expression for Q and S star? What is Q in this case? Q is D, S star. S. Okay. Does this already worry you guys? Is this sequential logic, or but just looking at this Boolean expression? So this is, what does this do? How can we change state for this DFF? Right? Hopefully, this is worrisome. This looks worrisome to you guys, right? This doesn't seem correct. we always stay at the same state. I haven't even talked about, right? So we haven't even talked about how to reset this thing. So, but it's gonna stuck at a certain state S, called S. There's no way that we can change the state. So what should be the correct expression for the Moore machine? What should be the correct Boolean expression for Moore machine for DFF? What's Q? We talked about this last time, S star. You can just write down the table, like truth table. What is Q? Anyone? We are coming back to the Moore machine, right? So I hope that most of you agree that this is not correct, right? This doesn't work. But let's come back to the Moore machine. So Q should be S star, right? S star should be what? What is S star? Again, just draw the table if you want. Anyone? What's S star? S star should be D. Right, of course, right? I hope this makes intuitive sense. Okay. This is clock edge, right? That trigger device. Okay. D, right? So then we D, right? It means the next state, right? Sorry. This should be S. S and D. Okay. I read it. I think one of you said S1, so that's why I put that star there. Right. Q should be equivalent with the current state, right? The next state should be D. Any objections about this? Right. So then let's come back to the mini machine. So so we actually talk about so one of the questions I asked you guys about item pool, right? Ask you about can we come up with a mini machine for the DFF? The answer is yes. We still need two states, right? Intrinsically we have two states, right? 0, 1, S0, S1. Okay, it's really about the transition and the output, right? So over here, 0, 0, no surprises, right? 1/1, right? What is this? 1, right? If input is 1, we output what? And if input 0, we output 1. Right, Steve, you're right. So we put 0 here and we put 1 here. Okay. And I'm gonna leave this to you as an exercise. Okay. Try to draw the transition output table and try to make sense out of this. Okay. And hopefully you guys will get the same Boolean expression like this. Okay. And you're supposed to see the same Boolean expression. So what does this tell us? This really tells us that actually for a Moore machine, right? If you look at DFF, it's actually a Moore machine, but we can represent it using either a Moore diagram or a MIDI diagram. So in fact, there's a way to convert Moore diagram into a MIDI diagram and vice versa. So this is actually not something that we're going to cover in our class, but later on, we are going to be clearly distinguishing two things. When I say Moore FSM or Moore machine, I'm referring to the actual hardware. We're looking at the hardware diagram and ask you, is it Moore or MIDI? Okay, so that's where we can actually check the connection of the output logic, right? And we can see whether there's a dependence on the input or not. But so if you actually want to draw it in a diagram, so in many cases, okay, actually in all cases, we can draw it using either Moore diagram or there's actually equivalent MIDI diagram, right? Any questions about this? I hope that you guys can actually try to make sense out of this. by writing down the truth table. Okay, and this is going to be a fun and also useful experience. Right? So we indeed need 2 states here with MIDI. But in general, okay, of course, this is the DFF, right? So we are looking at a specific problem, which is DFF. So in this case, the Moore machine and the MIDI machine, they have the same number of states. But in general, if you look at the complexity of the state machine, so indeed, MIDI machine tend to have fewer states in general because it's actually more expressive, right? Because you can put the outputs on the arcs. So this is a graph, right? You can actually have a n squared, right? N is the number of states, so you can have a n squared number of arcs, right? Between states. So this is indeed more expressive in terms of expressing different kind of outputs. But there are some pros and cons, right? With MIDI diagram, of course, with Moore as well. In our class, going forward for you guys to design your FSM, right? So we're going to be very specific with you. So I recommend Moore, right? So because Moore is indeed safer to use in the sense that the output always changes at the clock edge, right? It's not combinational. If you look at MIDI, it's actually reacting faster to the inputs because we output right away, right? So the output depends on the current state and the inputs. So if input changes, output changes right away. So basically, output is combinational, right, to the inputs. So which is, in some cases, is good to have, but in some cases, when we later on discuss how to calculate the clock frequency, this may lower the clock, may lower the operating frequency of your circuit. So this is one downside, right, of MIDI, because this combinational pass may turns out to be the long pass for us to determine the cycle time. So this is not something that we are going to discuss in this lecture, but it's going to be clear next time. And for Moore machine, it's in many cases more robust and more reliable to use in the sense that the output only changes the clock edge, and this may give us higher clock frequency. And also, there's something that you guys don't have to know, but when we connect, right, concatenate, when we put 2 communicating FSMs together with MIDI machine, we may have this sort of combinational loops. Again, this is something that we may look into in one of the later lectures, right? But for now, so just keep this in mind, right? So there are pros and cons, there are design trade-offs with MIDI. And I put a star in this slide. So this is basically optional. It's good to know, but this is not something that you guys need to know for the test, for exam later on. Right? Any other questions about FSM, MIDI machine and Moore machine? Or any other questions about the this exercise that we just did, the MIDI diagram for the DFF? Yeah, you guys can also draw the MIDI diagram for the TFF, right? It's going to be very similar, although the outputs will be different. But we do need 2 states. Okay. Mitchell is asking, is homework 4 on this stuff? Which stuff, Mitchell? More MIDI? Yeah, we will give you some questions about the FSM, both MIDI and Moore. All right. So let's move on. Okay, I just talk about clock frequency, right? Talk about timing, right? Talk about, right? So the MIDI may be faster and slower, right? But the thing is, we never really talk about the delay, right? So what do we mean by fast or slow, right? So we have been assuming that the gates, right, logic gates, basically take 0 time, right? So it's like we were living